Hello, I am Max Otute and welcome to our Logisim tutorial for CPU design. Okay, so we are going to be designing a 16-bit CISC CPU. CISC means Complex Instruction Set Computer. Yeah, so that's the purpose of this tutorial. And we are going to begin with the ALU, the Arithmetic and Logic Unit. So the arithmetic and logic unit is the component responsible for all the arithmetic, like the mathematical operations, and the logical operations, like all those Boolean and bitwise operations. Yeah. So I'm going to be using Logisim Evolution v3.7.2. So all project files will be saved with this program. I suggest if you are new to Logisim and you want to follow the tutorial, you use the exact version so there will be no compatibility errors. But if you already experienced with Logisim, feel free to use whatever you are used to. So let's add a circuit. Let's call it ALU. Okay. So now we are in our ALU circuit. So we are designing a 16-bit computer, meaning it's expected to be able to operate on 16-bit values. So we are going to take two inputs. Down here we have the properties, and for the properties of our first input, it's going to be 16 data bits, and we would prefer if we could have it shown in binary. Okay, and I'll just duplicate that for our second input. Let me move them here a bit. Okay, so I'm going to call this input 1, and I'm going to call this input 2. Yeah, so to add the labels, you can simply double click the component, or you can come down here to label and type it there. Okay, so now that we have our 16-bit inputs, let me extend the lines a bit. So these buses are 16 bits each. Alright, now we have our 16-bit lines for our inputs. Now let's look for the operations we want our ALU to do. So let's go to the arithmetic side. Now we want it to add. Adding is very basic. We want it to also subtract. We would like it to multiply. We would like to have division. Do we want negation? We could have it if we wanted, but for now we don't want it. We also don't want a comparator now. Do we want this? Well, okay, so let's have some shifting operations. So we would have a left shift and a right shift. This is logical left and this is logical right, and all of them are going to operate on 16-bit values. Okay, so there's 6 of them. Okay, let's add a few more. Let's have some purely logical operations like AND or. So we go to gates, we take an AND gate. Okay, we take an OR gate. Okay, and these will also be 16 data bits. Remember, everything which requires data is going to need 16 bits because our processor is using 16-bit data. So one thing you'd notice about these is that although they all take two inputs, there are a few differences. So with the add, you have a carry in, you also have a carry out. With subtract, you have a borrow in, you have a borrow out. With the multiply, you also have carries in and out. With the division, you have the upper, you have the remainder. With the shifting, you have the input to be shifted and you have the distance or the displacement. So for both shifts it's the same. Then for the logical, it's typical gate operation. So let's wire them up. Input 1, let's stretch the input 2. Let's take input 2 down here and let's wire all the input 2's. Okay, but with the shifting, the bits to be shifted, it takes a value which determines how many bits should we shift. So it won't be a 16-bit value because in 16 bits you can't shift 2 to the power 16 positions. If not, you're just going to get zeros after your first 15 shifts. So we would need just the number of bits required to express 0 to 15, which is 4 bits, right? So we will do these. We would have to take, let's go to wiring and let's get a splitter. Point this out, center it, bit width in 16 bits. Fan out will also be 16. Let's bring it a bit closer to them. And let's get another splitter. Let's point that north. Let's center it also. Bit width in should be 4. Bit width out will be 4. Okay, so what we are going to do here is we are taking just the first 4 bits of our second input and we are using that as our displacement. Now it's very important to remember the order of your operands because, for instance, A minus B is not the same as B minus A. It's very important to know the order when you are implementing your design. Okay, so let's extend the rest. And okay, let me shorten this. And let's add the lines for the first operands. Alright, so one thing is there's always an output. The output is going to also be 16 bits. Okay, because we are working with 16-bit inputs. So what we are going to do here is the ALU is given an opcode and the opcode determines which operation to do. So in order to switch between different results from different circuits, we are going to have a multiplexer. So plexes, a multiplexer, there we go. Now this is going to have 4 select bits and 16 data bits. Well, why does it have 4 select bits? Because we are going to be working with 16 operations, 16 major operations in our ISA. But if you realize our ALU only implements 8. So we do not need all 4, we just need 3 of them. Okay. So our max is going to take all the outputs into itself. Okay, so now we have all our outputs wired to our max, and we would want to write the output out, right? We are done with doing some calculation here. You'd expect that the result goes somewhere. So for that, we are going to have it connected to output pins. So we have an output pin. This will also, yeah, be 16, 16 not 17. Yeah, we would want to represent it in binary to have a better idea. Okay, so all right. Yeah, so our output is connected to whatever comes from the max, but the max select hasn't been scripted. Okay, so we have to add selects for the max. And what is the selection based on? It's based on the opcode that comes in. For instance, if the opcode is a 0, that means we are referring to an add. If it's a 5, so let's 0, 1, 2, 3, 4, 5, that will be a right shift. And for the ALU, it can take 8 operations, meaning 3 bits. So we are going to have another input. This input we are going to call opcode. This is 3 bits. Okay. And in order not to make our diagram messy, we are going to tunnel it. So we take a tunnel. Tunnels basically represent the wiring without you having to stretch all the wires. That's 3 bits. And we call this tunnel OPC. So when I bring OPC here, right now this isn't OPC, it's just an unnamed tunnel. Let's make that 3 bits OPC. So when I bring OPC here, what Logisim does is it's going to logically have these connected. So just imagine there was a cable going through to this side, but see how messy that becomes. So when you just have it tunneled, it's technically passing a cable from the entry tunnel to the exit tunnel. Okay, so right now we have an ALU which can take data and based on an opcode give us the wanted output. But there's one thing, what if we don't want to write the output at the moment? So we would have to control this, and to do that we would have a controlled buffer. So under gates, controlled buffer, and that's going to be 16-bit buffer. Now the controlled buffer is basically a regular buffer. The only difference is it takes a control input. Okay, this input, depending on whether it's a 0 or a 1, determines whether the buffer should allow data to flow. It's basically a diode in the electronic sense. So we are going to have to control our output somehow. So let's take another input, and we are going to call it output enable, OE for short. And we are going to tunnel this. We are tunneling it for the same reason as before. Let's call this OE. And this input is going to be, this is going to be a 1-bit input. If it says 0, do not write the output. If it's a 1, allow the output to go. So we just need 1 bit for that. Okay, so yeah, there you have that. Let's see, is our ALU finished? Not quite. Assuming we wanted to see our output without writing it, we would also want to patch that to a separate output. So for instance, this output will be, let's call this D out for data out, and then this is going to be stored result. Stored result basically means the result that came from the operation. Let's make that 16 bits binary. Okay. Okay, so let me shift everything a bit. There we go. Okay, so let's test this. To test it, we just need to click this, which allows us to change values within circuit. So for instance, let's add 2 and 3. So what's 2 in binary? 2 is 1 0. That's 1 0. And 3 is 1 1 1 1. And the opcode for add is 0. So these will all be zeros. So when you come here, you see that the data goes through all of them alright, and it comes to the max, and based on the opcode it determines whose output we should take out. So right now, since it's on addition, the max takes 0 0, as you can see, 1 0 1, which is 5, and that's true because we added 2 and 3. Say we wanted to multiply 2 and 3, that would be opcode 2. So we would make this 2, and you see that we get 1 1 0, that's 6, which is indeed the product of 2 and 3. So take some time to just play with this a bit and see the whole flow of data and everything. It's very simple. Okay, so one more thing is, aside just what we've done, remember the carry ins and carry outs. Now I'm not going to implement those for now, but since we'll be implementing jump instructions which would have conditional jumps, we would want to have the flags though. So to get the flags, we are going to have to work with these. For instance, if it's a carry flag, the carry flag is set if there is a carry. So for instance, if you added something and there was a carry out, your carry flag would be set. With the subtraction, if there was a borrow out, you'd also have that. For multiplication and division, we would not be doing that. So we are just going to make a carry flag for both addition and subtraction. Okay. So let's get a splitter. So bit width in should be 16. Fan out should also be 16. Let's have it centered. Okay, the purpose of this splitter is to take the output and give us all the individual lines of the output. So you can see that when we connected it, it's showing us 1 0 1 0 0 0 0, just as it is here. So we are getting the individual lines of the output. Why do we want the individual lines? Because we want to check some things based on these values. Okay, so let's implement a zero flag. The zero flag is considerably the simplest to implement. Basically, it's set when the result was a zero. Alright, so how do we check if it was a zero? We can NOR all the bits. So let's take a NOR gate and let's make it smaller, face south, and our bit should be 16 of them. Oh wait, the data size should be 1, but the number of inputs should be 16. Yeah, there we go. Okay, so now we just need to pair these up. Remember, it's a NOR gate. The NOR gate gives us a 1 if after ORing and then negating the result, it got a 1. So if after ORing all the bits, it gets a 0, then the NOR gate will give us a 1. And that's exactly what we want for the zero flag. We want the zero flag to be set if after the operation the result was 0, which means all zeros. Okay, and we can push that out to an output we are going to call our zero flag, ZF. Okay, so with our zero flag done, let's move to our carry flag. Now with the carry flag, remember, it doesn't apply to all the operations, it applies to just some of them. So what we are going to do is we would need to not just know which operations it applies to, but we would also need to find a way of checking the particular one within those allowed operations that we are working with. So let's take a max. This max is going to have so let's see how many operations can give us carries. we have just 2 here, we have addition, we have subtraction. So we are going to have a 2 input max, which the default is already 2, and we have select bits, which is to identify which becomes output. So for instance, if it's 0, if the select is 0, we would expect the adds carry out to be pushed through, and if the select is 1, we'd expect the subtraction borrow out to be pushed through. So let's connect the data. So what determines who gets pushed? Well, if you realize, when the opcode is 0, it means the add should get pushed. When the opcode is 1, subtract should get pushed. So what we are going to do is we are going to go to our opcode right here. Okay, so let me put this above. I'll move this a bit. Okay, so we are going to split our opcode. Yeah, there's a whole lot of splitting going on. It's 3 bits, and we want 3 bits out. Okay, so this gives us the 3 individual bits of the opcode from 0 to 2. Now we want to check if it is indeed an addition or a subtraction operation. So to do that, we are going to work with these 3 bits. Addition and subtraction only depends on this bit. So if any of these bits have the value 1, we know that it is not what we want. So for that, we can use a NOR gate. Let me have some space. Let's set space into 2. Okay. So we get a NOR gate face south. Yeah. Let's make that narrow. Okay. Okay. So from this you can see that since both of these are 0, we get a 1. The 1 here is going to be necessary later on. So now let's move to this side of things. Right now we've selected which input we want. Now we need to determine which of them is actually coming out. And since add is a 0, subtract is a 1, we are going to be working with this bit. So we are just going to directly connect this bit to it. So now our output comes, but we don't want to set the flag unless it was an add or subtract operation, which is where this becomes important. Okay, so we are going to take gate and end gate. Let's make that narrow. Falling. And the output of this AND gate is going to be a carry flag. Now we are left with a sign flag, or what people call a negative flag. Basically, as the name implies, it tells us whether the result was positive or negative, whether it was a signed value or not. So let's zoom out a bit. Now, in order to check if the result was positive or negative, now with these bits, when you get a negative value, for instance -1, -1 will be represented as all F's. Now all F's also could imply that you have 2 to the power 16 minus 1. But in a signed representation, all f's would imply a negative 1. So to check that, we simply need to check if the last bit has a high value or not. Okay, so if the last bit is a 1, by last I mean the most significant bit. If the most significant bit is a 1 in a signed representation, that means our result was negative. So let me put an output pin for our negative flag NF, or you can call it SF for sign flag. So we are looking for our last value here. Okay, but there is one thing though. Well, so I've created an issue here. There's a collision here. That's not what we want. Let me undo that. Let me pass it around this way instead. Okay, so this now tells us whether the result of our operation was negative or not. Okay, so this is our ALU. Take some time to go through it and understand all the parts of it. Alright. In the next video, we are going to create our general purpose registers or register bank.